Every year, over 1 million students in India sit for the Joint Entrance Examination, or JEE. It is one of the most mathematically rigorous and fiercely timed physics assessments on the planet. Inside preparation hubs like CODA, students train under extreme pressure. They solve multivariable mechanics problems in 2 to 3 minutes, a fraction of the time typically allowed in standard university physics courses. Admission into elite engineering institutions, the IITs, requires more than just high-speed calculation. It requires a complete departure from standard mathematical pathways. Surviving an exam engineered to break you requires a distinct cognitive strategy. Brute force calculations are often the longest possible route to a solution, and in this intense environment, time is the primary constraint. Success in competitive physics depends on identifying the underlying symmetry or constraint that renders the standard calculation completely unnecessary. When you attempt to solve multi-body physical systems from a static ground frame, the mathematical overhead is massive. You are forced to track overlapping accelerations, continuous forces, and relative displacements simultaneously. Resolving these chaotic systems requires a different lens, one that collapses the physical geometry into simpler algebra. By analyzing the preparation material for this exam, we can extract 3 highly effective frameworks: non-inertial reference frames, energy heuristics, and kinematic boundaries. Today, we will deconstruct 3 specific mechanical systems to demonstrate how shifting frameworks reduces a problem to its simplest components. We begin with a block of mass m released on a frictionless inclined plane. Simultaneously, the plane itself is accelerating to the left at a constant rate, a0. Tracking the block's displacement from the ground requires measuring both the wedge's horizontal translation and the block's relative slide down the angle. These 2 vectors combine into a complex, non-linear path. Locking the observer's coordinate system directly onto the accelerating wedge simplifies the geometry. From this perspective, the degrees of freedom are reduced. The block simply slides in a straight line down the slope. However, because this new frame of reference is accelerating, it is non-inertial. Newton's second law, the familiar F equals ma, cannot be applied directly. To restore the utility of Newton's laws, we apply a mathematical correction, the pseudo-force vector. We assign the block an artificial force equal to its mass multiplied by the wedge's acceleration, pointing in the opposite direction. Projecting these forces along the incline reveals the relative acceleration. Gravity pulls down with mg sine theta, while the pseudo-force pushes back with ma0 cosine theta. Because this relative acceleration is constant, calculating the time to reach the bottom is now a single-step kinematics calculation. Adopting a non-inertial frame is a strategic trade. You accept the conceptual overhead of a pseudo-force to eliminate the complex vector tracking of the ground frame. In our second system, Bob A drops from a 60-degree angle to elastically collide with Bob B. Bob B must then inherit that momentum and complete a full vertical loop of radius r. A common pitfall is attempting to find Bob A's impact velocity by integrating the tension force of the string throughout its arc. Tension is always perpendicular to the block's velocity vector. Since the dot product of force and displacement is 0, the string does 0 work on the system. If we ignore tension and look at gravitational potential energy, the velocity is dictated entirely by the vertical geometry. For a string of length L at 60 degrees, the vertical drop is exactly L minus the cosine component, or L over 2. Equating this potential energy loss to the kinetic energy gain reveals Bob A's impact velocity is the square root of GL. In a perfectly elastic collision between identical masses, the velocities swap. Bob B inherits the velocity instantly. To complete a full vertical loop without going slack, Bob B's bottom velocity must be at least the square root of 5gr. Equating this boundary to the inherited velocity defines the exact ratio between string length and loop radius. Energy heuristics allow us to bypass continuous, non-working forces and calculate the end state of a system based entirely on vertical displacement. Our final framework addresses a systemic error in how physical boundary conditions are defined. This particle's position over time is defined by the function 4t cubed minus 3t. Its instantaneous velocity is the derivative, 12t squared minus 3. Identifying the exact moment this particle reverses its physical direction requires more than just finding a zero state. Students often assume a turning point occurs wherever velocity is zero, which in this case is at t equals 1/2. A velocity of zero is a necessary condition, but it is not sufficient to prove a change in direction. A particle can slow to a complete stop and then continue accelerating forward. A true reversal requires the velocity function to completely cross the temporal axis, changing its sign. In our function, the velocity at t equals 1/2 moves from negative to positive. This sign change only occurs if the acceleration is non-zero at that moment. The acceleration must actively pull the particle into a new direction. Boundaries in physical systems are determined by the behavior of their derivatives. A zero state is merely a candidate for a turning point. The sign change is the proof. We analyzed 3 complex physical scenarios by looking past their immediate mathematical complexity. Shifting into a non-inertial frame eliminated the need to track multi-body vectors. Applying energy heuristics ignored non-working forces. And requiring a derivative sign change provided rigorous proof for kinematic turning points. Physicists use these same cognitive lenses to translate raw, chaotic observation into mathematical logic. Intuition is the ability to identify the invisible, invariant rules binding a chaotic system before the first equation is ever written.